Hi, Math 30-1. Today we're going to go into Lesson 3 from applications of exponential and log functions. So we're going to talk about applications with exponential growth and decay. So this is found in your workbooks on page 249. Okay, so lesson 3. So just to review, an exponential function is an equation equal to y equals a b to the power of x, where a can't be 0 and b is a positive number and x is element of real numbers. And just remembering when a is greater than 0, if b is greater than 1, then it represents growth, right? So increasing exponential graph. And if our base is in between 0 and 1, the function represents decay, so a decreasing exponential function. Okay, so we're going to be using that equation and applying them to word problems. So many applications of exponential functions in real life. In some cases, the function y equals a b to the power of x can be written in disguised form. So for example, they can change it to become a equals p, 1 plus I is an exponential function. So the base this time is 1 plus I. So this lesson, we're going to look at growth and decay. So we can use variations of the formula y equals a b to the power of x to solve problems involving population growth, bacteria, and radioactive decay. So those are kind of the typical contexts that we work with. Okay, number 1. So in 2012, the university population of a country was 160,000 and was increasing. So that tells you that B will have to be greater than 1 at an annual rate of 4.5%. So if the function representing the population is of the form y equals a b to the power of x, state the values of a and b. So a will typically be your initial value. So in this case, we started with an initial population of 160,000. And then our b, we know, has to be increasing by 4.5%. So first of all, 4.5% as a decimal is 0.045. But if I use a b value of 0.045, that would actually represent decay. So in order to make sure that the population is always increasing and carrying that initial amount forward every time, we're going to throw in a 1 in the front. So our b will be 1.045. So again, the 1 carries over that previous population amount, and the 0.45 is the 4.5% increase. Okay, part B. Write an equation to represent the university population P of the country as a function of the number of years n since 2012. So they've just changed our variables to be in terms of p and n. So our equation will be population is equal to 160,000 for A times our b value, 1.045 to the power of n. Determine the population in the year 2015. So the equation we came up with is for the year 2012. If I want to look at the year 2015, that means my n will be 3 years later. So just substituting n to be 3 and straight evaluation. Okay, so 3 years later, or in 2015, the population will be 182,586. Okay, and part D, if the population continues to grow at this rate, determine the number of years to the nearest year for the population to double from its 2012 size. So 2012, the population was 160,000. Double that. So if I go 160,000 times 2, we want the population to grow to be 320,000. So that will be our final value of P. So substitute it in there. Starting out 160,000 growth 1.045. And this time we're solving for n. So this is what we practiced back in lesson 1. So starting out by dividing by 160,000, which is 2. And we have 1.045 to the power of n. We'll log both sides to solve for our exponent. Bring the exponent down using the power law. And then just simply divide. So you're going to go log 2 divided by log 1.045. And we get 15.747 years. And they said determine the number of years to the nearest year for it to double. So in order for it to double, I would round this up to 16 years for the population to double. Okay, so we came up with an exponential equation and then solved it using our logs. Okay, let's go ahead and try number 2. So if the number of fish in a lake is decreasing, so that means that our base will have to be in between 0 and 1 by 5% each year as a result of overfishing. So if the number of fish present is an exponential function of time, state the base of the exponential function. Okay, so this time it's a little bit different. So if it's decreasing by 5%, that means that every year there's 95% of the population remaining, right? So if I go 100% minus 5%, that means every year there's 95% of the fish population remaining, which is going to be my base number. So my base as a decimal will be 0.95 to represent 95% of the population remaining and to represent decay because that b value is in between 0 and 1. Part B, write an equation to represent the number of fish present after t years if NO is used to represent initial population and N of t to represent final. So just the equation. So final equation N of t, or final amount of N of t is equal to our initial times our base, which we just found, 0.95 to the power of time in years. If there are 2,500 fish present in June 2012, how many would you expect to be present in June 2017? So we're looking for our final. So starting off with an initial population of 2,500, 0.95. So that initial population was in 2012. We want to know 5 years later, so t will be 5. So our n of 5 will be 1,934 fish. Okay, and then for D, how many years to the nearest tenth would it take the fish population to reduce to half of the number in June 2012? So June 2012, we started out with 2,500. If I divide it by 2, I'm looking for there to be 1,250 fish. So that will be my final population that it's reducing to. Starting at 2,500, 0.95, and we're solving this time for time. So again, divide, which is a half. Solving for our exponent, we'll use our logs. So log a half, bring our exponent down, power law, log 0.95, and then just simply divide. So log a half divided by log 0.95. So we get 13.5134. So how many years to the 10th? So this would be 13.5 years to reduce to half. Okay, so that's an example there for decay. That's number 2. Number 3, again, it has that natural log, so just omit class example number 3 And at this point, I'll give you a chance to do some practice with the ones there from the homework, so 1 to 7. Okay, hopefully you had a chance to do some practice. Let's continue here on 251. So we're going to take a look at half-life, doubling time, etc. So half-life, the formula is used when we want to talk about something decreasing. So all this stuff here just kind of talks about it. So the exponential function that we use to represent half-life will have a base of 1 over 2. So this is the formula that we'll be using here for half-life. So just in terms of what everything represents, so AO will be your initial, A will be your final, half-life means that it's decay, so this is decay because it's between that 0 and 1. Okay, then for your exponents, it's 1 over h and then t. Actually, we should probably be looking at it over here. Okay, so they just simplified it here. Okay, so again, initial, final, half-life, and then time, and then h on the bottom is half-life. So this is half-life. So they'll say the bacteria has a half-life of 5 days, and this will be time. And the thing that's special about the time and the half-life is that these will always have to be, or they will be, the same units. So if half-life is given to you in hours, then time will be in hours. If half-life is given to you in days, time will be in days. And oppositely, if time is given to you in days, half-life will be in days. So those units will always be the same. So that's the half-life formula. And then similarly, we have one for doubling time. You'll notice here that this time the base is greater than 1. So we have, again, AO for your initial of whatever you're talking about. A is your final. B is this is for doubling because B is greater than 1. And then we got time again on top. And the D is doubling time. And again, same units for T and for D. Okay, so those are the two types of formulas we're going to use when we're talking about growth and decay, so specific formulas for them. So let's go ahead and try class example number 4 on the next page here. Okay, so a patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. 24 hours later, the sample was recounted and was found to contain 8,012 cells. Find the doubling period, okay, so that's the formula, of the bacteria to the nearest tenth of an hour. Okay, so we're looking to use the formula for doubling. So from that previous page, AO, 2, and T over D. Okay, so final amount of bacteria, we want it to grow to be 8,012. We started with 387. 2. Okay, they told us that this took 24 hours, so that's our T. And we're looking to solve for doubling. Okay, so solving for our exponents. So first thing we're going to do is divide by 387. So 8,012 divided by 387 is 20.7028. And then 2 to the power of 24 over D. Let's take the log of both sides to solve for our exponent. Move that exponent to the front. And we're left log 2. Okay, then we'll divide by log 2. So log of that 20 divided by log 2, which is 4.37175, 24 over D. And variables in the bottom. So this is where they do that switch. So you're going to go 24 divided by 4.3717. So everything should be in your calculator stored, all those decimals. Okay, so the doubling time to the nearest tenth of an hour is 5.5 5 hours. Okay, number 5. In April 1986, the nuclear accident at Chernobyl contaminated the atmosphere with quantities of radioactive iodine. If the half-life, okay, so formula, of radioactive iodine is 8.1 days, determine the number of days to the nearest day it took for the level of radiation to reduce to 2% of the original amount. Okay, so this time we're using half-life formula. So base should be a half, T over H. Okay, so we want to reduce it to 2%. So that means if I start out with 100, I want to go down to 2. Okay, and they want to know how many days that takes. So I'm solving for time. And the half-life, so H is 8.1. So again, start off by dividing by 100. I'm going to just put this as a decimal, 0.5, T over 8.1. Then we'll log both sides. Okay, then we'll go log 0.02 divided by log 0.5, which is 5.64385. T over 8.1, and this time I'm just going to multiply the 8.1 up. So taking that decimal in your calculator times 8.1, and you should get 45.7152. And they said how long to the nearest day, so this would take 46 days. So same units as that half-life that they gave us originally in the question. Okay, and number 6. So radioactive isotope has a half-life of 7 years. Use the formula A equals AO CT over P, with our base being 1 over 2, because they said it's a half-life, so base of half, to determine how much of the isotope must be initially present to decay to 60 grams in 14 years. Okay, so using that formula, we have A equals AO, 1/2, and then T over P. So notice just no special variables for that T and that P, but it's a half-life form question here. So we want to know initially present. So we don't know our AO, but we want it to decay to become 60. So that's our A, 1/2. So they said this takes 14 years. So that's time. And P being our half-life, which is 7. So just putting it in different context here. So let's evaluate 1 over 2 to the power of 2. So 1 over 2 to the power of 2, which is 0.25. Okay, and then to get AO by itself, 60 divided by 0.25. So the initial amount would have had to have been 240 grams. Okay, write an equivalent formula, this time with a base of 2, which would solve the problem in A. So if I change this to base 2, how would that look? Okay, so if I took this here, this formula, and changed it to base 2, this would become 2 to the power of -1, all to the power of 2, right? Base 2, so just practicing change the base. So then this would be AO, and then 2 to the power of -2. That's what how it would look like. Okay, so that takes care of the lesson there for lesson 3. So questions in the homework are just related to using the exponential equation or the half-life or doubling time formulas.